All right, so begins lecture 30, which is on the calculation and properties of gradient, curl, and divergence. This is roughly from pages 329 to 332 in the 2020 notes. As you can see, I have a printout of a previous year's notes. You'll forgive me, but they're in color, so woohoo! Anyway, so basically this is a discussion about this operator right here, del, or sometimes nabla. All right, nabla. And like the tech for this, I think is backslash, I guess, nabla probably. But anyway, first of all, we've already talked about this, but if you have a function, you can calculate nabla f, or the gradient of f, by just looking at the vector of partial derivatives, right? So we can start with a function and we can create a corresponding vector field by calculating the gradient, right? We already know how to do that, and I've even showed you how you can do that sort of natively, naturally in polar coordinates or cylindrical coordinates or even spherical coordinates, right? It's good for us here to have a nice compact formula for it. And so that is in 3 dimensions what's, right here, right? Fine. But well, here's also in 3 dimensions. I equals 1 to 3, partial IF, x hat, x sub I hat. So this is a nice, I'll need this formula for proofs in this section, all right? So first of all, just to point out some obvious things is, and I don't know if I ever pointed this stuff out before in this course or not. Maybe I failed to. I probably did in the notes. I don't think I talked about it in any of our lectures. My bad. But if I didn't. But it is true that the the gradient of a sum is the sum of the gradients. You can pull constants out, and of course you also have this product rule, right? So these are all the properties of the gradient operator, which are useful to know. In fact, from an abstract mathematical perspective, this makes nabla what's called a derivation. A derivation is a linear transformation, which is, well, it's linear, it's additive and homogeneous in that sense. And it also has the product rule. If you have those 3 things, then that function, that map, is a derivation. And next up, and by the way, I'm not going to really motivate why we're looking at these operations. So the philosophy here is to show you how to calculate gradient, curl, and gradient, divergence, and curl. And then we will spend the better part of, I don't know, 3 or 4 other lectures exposing the geometry of these. It is not obvious why I'm doing this. At the moment, you just have to accept this is something we can do. Eventually, I'll explain that basically it is what it sounds like. The divergence of a vector field sort of describes how the vector field's spreading out. The curl of the vector field, in some sense, describes how the vector's curling around points. But those need a lot of qualification, and that qualification only properly comes with a full exposition of Green's theorem, Stokes' theorem, and even the divergence theorem. So the central theorems of this part of the course actually expose the geometry underlying these operations. But we're not doing that today. Like today, we're just going to look at this is the divergence. So to calculate the divergence of a vector field, formally, you take the dot product of the gradient operator with the vector field. This is just a mnemonic, if you will, popular in physics and science and engineering. But the divergence of a vector field is partial f1, partial x, partial f2, partial y, partial f3, partial z. In the PQR notation, it's partial p, partial x, plus partial q, partial y, plus partial r, partial z, if this is for f equal to PQR, And of course, the divergence could also be calculated in n dimensions. Just the same, right? Because we can calculate a dot product in n dimensions by just taking the weighted sum of the products of the components from 1 to n. Well, it's not even weighted. There's no weights in the dot product, right? But anyway, so a nice, slick, quick formula for the divergence is given here. The divergence of a vector field is the sum I equals 1 to 3 of partial I fi, right? And the divergence also has nice properties, as you can easily prove following from the corresponding properties for partial derivatives. The divergence of a sum is the sum of the divergences. You can pull a constant out, and you even have this product rule of sorts here. Notice that, goodness gracious, all of a sudden. So the divergence of a function times a vector field, f is a function, g is a vector field. It's the dot product of the gradient of the function with the vector field, and then the plus the function times the divergence of the vector field. All right, so this is the product rule of sorts, but this is the scalar multiple of f by g. All right, so we can't, at least in the arbitrary context, how do you multiply vector fields, right? Well, okay, there is a way. We could take the curl of two vector fields, right? So maybe one of the other things we should ask is, okay, so if that's how that works, what is the divergence of f cross g? Like, how would that work, you know? That would be a natural question to ask, and maybe I'll ask that and answer that. We'll see. I don't know if I have that in the notes or not. Let's find out. But anyway, here's a proof of both this the additive and the homogeneous property using the notation I've introduced. So the divergence of f plus cg is the sum I equals 1 to 3 of partial derivative with respect to xi of the ith component of f plus cg, which is fi plus cgi. But then, by properties of finite sums, I can break up the finite sum into the sum of the sums and pull out the constant, and then that's exactly the gradient of f, and that's exactly the divergence of f, and that's the divergence of g vector, right? And so there's that linearity of the divergence, and the proof of this is similar. I might have made that a homework, so I have not proved that one, but it would follow from the product rule. Tell you what, I'll do it right here. So if I can fit it in, I'll try to fit it in right here. So how would we prove that? Well, the divergence of the function f times vector field g is equal to the sum I equals 1 to 3 of partial I of f function times g vector ith component, right? But what is that? That is the partial I derivative of the function times the ith component of g, right? Because that's the ith component of f times g is just that. But then that, by the product rule, is the sum I of partial if times gi plus f times partial ig, right? I. But that is nothing more than the gradient of f dotted with g, and this is f times the divergence of g. I mean, there's probably one more step I should include here, to be careful at the level of my to make the level of detail in my proof uniform, let's say. But I'm just going to do that much because I'm kind of running out of room. But there's a flavor of how you would prove that product rule. All right, and so next up, of course, we can take the curl of the gradient operator with a vector field. Curl f is nabla cross f, which is this, combination of 6 partial derivatives, the z component with respect to y minus the y component with respect to z, the x component with respect to z minus the z component with respect to x, the y component with respect to x minus the x component with respect to y. In every slot, we are looking at derivatives of components that are not in that slot. So like the x slot involves derivatives of y and z components with respect to y and z. The y spot considers derivatives of x and z components with respect to x and z. And the z component involves x and y components with respect to x and y. And, So just like the curl, there's that sort of complementary property that the component doesn't involve the actual same component of the vector fields which construct it. Now in this case, it's not. Nobble is not a vector field; it's a vector of operators, and F is a vector field, right? But of course, notice that the curl is a new vector field. In contrast, right, the divergence was a function, right? The dot product of nabla and F gave us a new function, give us a new function, and then the gradient took a function and made it into a vector field. So the gradient, both the gradient and the divergence change the object type, but the curl takes a vector field and spits back a vector field again at you. All right, so let's see here. Here's a snazzy, wonderful formula for the curl in terms of the Levi-Civita symbol in 3 dimensions. Epsilon ijk, remember, epsilon 1, 2, 3 equal to epsilon 2, 3, 1 equal to epsilon 3, 1, 2 equals to 1. Epsilon 3, 2, 1 equal to epsilon 2, 1, 3 equal to epsilon 1, 3, 2 equal to minus 1. All others 0. So that captures the 3 positive and the 3 negative terms implicit in the cross product elegantly, compactly, as that nice formula right there. And that's the partial derivative of the jth component function of the vector field with respect to the ith coordinate there. And then, of course, curl likewise has linearity, it has additive, it has homogeneous, and it also has a product rule of sorts. Scalar function times g is gradient of f crossed with g plus f times the curl of g. So that's pretty neat. We have these corresponding properties for the curl. And the proof of those is very similar to the one I just showed you, except it has to be married, if you will, against the epsilon ijk formula. Here's an example proof of the linearity. So like the curl of f plus cg is, let me zoom in a bit because I know it's hard to see these indices. There we go. So the curl of f plus cg is sum of ijk from 1 to 3, epsilon ijk, ith derivative of the jth component of this, which is of course fj plus cgj, times the x hat k, to put it in the kth coordinate. And then, well, by properties of partial derivative differentiation, I can break the sum up and pull the constant out. And then likewise for the finite sum, I can break the finite sum, the sum of the finite sum of sums into a sum of the sum of finite sums. Anyway, properties of finite sum, I can pull the constant out and break up the addition. And then, of course, you tilt your head and squint and go, wait a minute, that's exactly the curl of f, and that's exactly the curl of g times c. And that is the linearity of the curl. So there you have it. And the other property here, I've probably made a homework, at least in some year, so that's why I don't have a proof in the notes, but it's a good homework problem to prove that. And I just point out that, so this is very, it gets you really, really confused if you're not on your toes here and ready for, what's going on, because this notation is sort of seductive in some sense to bad thinking. Like a dot b is equal to b dot a, right? That's a property of the dot product of vectors, but also vector fields. However, the divergence of the vector field A is not equal to A dot del. Like, it can't be. See, because this is on the left-hand side, we have a function, right? It's like the x component of A with respect to x plus the y component of A partial differentiated with respect to y plus the z component of A partial differentiated with respect to z summed together. That's the divergence. The natural interpretation of this would be like a1 partial x plus a2 partial y plus a3 partial z, right? I mean, that would be the natural interpretation of that notation, a dot del. And a dot del then is an operator. You can't have an operator equals to a function, right? That's not reasonable. So it is true that the dot product of like objects commutes, but you got to be careful. Just because we can use dot product notation to succinctly describe the divergence, it doesn't mean that it is a dot product in the same sense as that. And so you can't use properties of the dot product of vector fields to also manipulate the divergence of a vector field. It just doesn't. It's not true. All right. Now, now for some. Now here's to use this is a grown-up theorem. These these are not easy. Oh, look, I do have the divergence of a curl. A divergence of a cross product of two vector fields. It's the dot product of G with the curl minus, interestingly, F dot the curl of the other vector field, right? So G dot the curl of F minus F dot the curl of G. The gradient of a dot product of two vector fields is these four terms. Yowzers. So the curl of F with the curl of G, G cross the curl of F, minus the operator F dot del, like we are just talking about A dot del. This would be F1 partial X plus F2 partial Y plus F3 partial Z acting on G, plus G dot del acting on F. Wow, that's quite something. And then the gradient of a this doesn't even make sense. I think that I'm missing a curl right there. Let's hope so. All right. And so yeah, here's some proofs. So the when you calculate the divergence of the curl, rather when you calculate the divergence of the cross product, that means we're taking the kth derivative of the kth component of the cross product, right? But the kth component of the cross product is given by the sum over epsilon ijk of fi jk. Epsilon ijk is a constant. We can pull it outside the derivative. And then we've got the derivative of the product of fi and gj, which by the product rule is the kth derivative of I times gj plus fi times the kth derivative of gj. And then what I did here was I kept the epsilon ijk for the first term, fine. And then I said minus fj e epsilon I k j partial I g k I j I k j. It looks like I flipped the j and the k. I'm not sure. It seems like it more naturally there would be. I'm not sure this is a mistake, right? Okay, I could be forgetting like some kind of internal logic here, but I would more naturally put fi epsilon I k j partial k g j from the line above. So yeah. Not sure why I did that. In any event, if I did, I mean, I'm not sure why I put the letters the way I did there. The minus is because I flipped the kj, like epsilon ijk is equal to minus epsilon ikj. All right, that's the nature of Levi-Civita symbol. And if you know, just let's suppose that that's a typo for a second, right? It probably is, because there's a missing index on the next term. I think that this maybe got lost in translation. I'll blame the students. I had tech things up. I'm sure it was the students. But the sum over kj, this is exactly the curl of G. This is the ith component of the curl of G, is what that is. And of course that's, you know, the ith component of F. And if you take the sum of this times that, that's F dot. So like, first of all, I'm missing a J here. If this is a J, I should have a J there. So what I might have done is I might have just flipped. I might have like changed some summation, relabeled the summation index, but well, anyway, let me not belabor it anymore. That should be a k if this is a k, and then you've got g dot curl and minus f dot curl. So anyway, in summary, maybe there's like a small typo in there, but that's basically the spirit of how you can. Actually, that's not the spirit. This is the gory details of how to prove it. If I was going to give you the spirit of the proof, I would just say, well, the curl is linear, the dot product is linear, partial differentiation is linear, and so when you put them together, it works out. And then you gotta switch some stuff around. That's where the minuses come from, right? Now the proof of the other, the proof of the other two things I think are homework problems, solutions of which I think I have posted online actually. Anyway, and then you also have these well-known identities. They're actually very interesting and important. So the dot product of the curl is 0. The curl of the gradient is 0. And the curl of the curl ends up being related to the Laplacian in this way. It's actually the gradient of the divergence minus the gradient. It's the nabla squared of f. That would be like nabla squared of f means nabla squared is like partial squared, partial x squared, plus partial squared, partial y squared, plus partial squared, partial z squared in 3 dimensions, etc. It's also called the Laplacian. Although, depending on what you read, the plus or minus the Laplacian, let's say, plus or minus is depending on what you're reading and what audience, I mean, what author you're looking at. The third one, though, is very interesting. Let me explain to you what how it's important to the laws of physics. So these are Maxwell's equations right here in the absence of sources. In the absence of charge or current, these are the differential equations that describe electromagnetism. The divergence of the electric field is 0. The curl of the electric field is minus the time derivative of the magnetic field. The divergence of the magnetic field is 0. The curl of the magnetic field is the permeability times the permittivity times the time derivative of the electric field. So these 4 equations are collectively known as Maxwell's equations. And again, these are special in the special case of no charge and no current. When there's charge and current, there's other terms that come into play, corresponding to, say, Gauss's law, Ampere's law, or rather Ampere's law, or Faraday's law. This is actually Maxwell's correction to Faraday's law. Anyway, so cool thing, if you calculate the curl of the curl, right? Well, the curl of E, right here, is the time derivative of B, right? And but on the other hand, the curl of the curl is the nabla of del E minus del squared, the Laplacian of E, from part 3 up here. Now the divergence of E is 0, and then and on the other hand, I can pull the time derivative out here. So I pull this time derivative out, and then that gives me time derivative of the curl of B. But the curl of B, remember, is mu naught epsilon naught partial E partial t. So what that gives us then is that nabla squared E is equal to mu naught epsilon naught partial squared t. And if you've had a lot of physics, you'd recognize that this is saying that the second derivative with respect to space is proportional to the second derivative with respect to time. This is what's known as a wave equation. And more than that, it's a wave equation where the coefficient in the wave equation describes the speed of the wave. And you can do the same thing for the magnetic field, and the magnetic field satisfies the same wave equation. All right. And for both of these, the speed of the wave equation is the speed of the wave is 1 over the square root of mu naught epsilon naught. That's the permeability times the permittivity of free space. Now, this, if you work it out, is 3 times 10 to the 8th, roughly speaking, meters per second. In other words, from Maxwell's equations alone, and this vector identity right here, we can derive that the electric and magnetic fields satisfy a wave equation, and the speed of the wave equation is nothing more than the speed of light. And that speed of light actually depends just on the properties of space itself, namely the permeability and permittivity of space. This is shocking, because this is what made people think that there's something called ether. So the luminiferous ether was something we searched for back in the 19th century. All right, you be quiet. Yeah, I've already told them not to call back, so oh well. Getting back to the lecture here, this is very interesting because it says with Maxwell's equations and this vector identity that the electromagnetic fields satisfy a wave equation and the speed of the wave equation is constant. And that's very interesting because that suggests that the speed of light apparently doesn't depend on the choice of, I mean, how does that happen? That the speed of light just depends on mu naught and epsilon naught, which are properties of space and time itself in some sense. This is very, very interesting. And so there were, one of the dominant things that was done in physics is they said, well, there's this luminiferous ether, that's the medium through which the light is waving, and so if that's true, then we should be able to see that there's a difference when the sun is when the Earth is going through the ether on one side of the sun versus the other. And there was something called the Michaelson Morley experiment, which was done back in about the late 1890s or early 1890s, somewhere in there, and it was done very carefully, and there was no evidence of the ether found. So then, what to do? Well, that was left to Einstein. Einstein said that, in fact, basically he said, well, nope, these equations are right. Light does solve these wave equations. The speed of light is this constant, and that is basically one of his axioms for what's called special relativity. So I'll stop there, but this is, I think, very interesting physics that is revealed to us simply from vector calculus. Now, I don't guess I have... oh, here's the formula for here's the proof of the curl working out to the Laplacian. So, brute force, it would take a while, and I'm sorry I don't seem to have any, actual examples here. I'll do an actual example for you. Gradient of x squared, y cubed, z to the fourth. All right, let's see here. This would be partial x of x squared plus partial y of y cubed plus partial z of z to the fourth. And so the answer is 2x plus 3y squared plus 4z cubed. That's a sample divergence calculation. We've already done gradient calculations, so I won't do another one of those for you. But I'll do a curl example. Let's calculate the curl of, say, y squared, z, and 3. So here's a fun help for you. One of the mnemonics you can use, and this is in all the calculus books, you put like x hat, y hat, z hat up here, then partial x, partial y, partial z, and then your vector field y squared, z3. I mean, you can think of the curl like that. And so what it really is, of course, is what I'm about to write. So the y derivative of 3 minus the z derivative of z, comma, the, let's see, y hat minus y. So partial z of y squared minus partial y, or rather partial x. Remember, this should not involve y directly. It should involve the y components or the y derivatives. It can involve, I mean, if there's a y squared here because that was the x component of the vector field was y squared. Anyway, partial x of, sorry, I lost my place. Y hat, partial z, y squared, is partial x of 3. And then z hat, partial x of 3, minus partial y of y squared. All right, so the curl, if I haven't made a mistake, which is, you know, anybody's guess, is that's 0, that's 1, minus 1. Partial z of y is 0, partial x of 3 is 0. And partial the derivative of 3 with respect to x is 0. Partial derivative of y with respect to y squared is 2y, so that's minus 2y. And so there you go. There's the curl of this particular vector field. All right. So don't say I didn't do any examples, but definitely my focus here was more on you know, like theoretical properties, and I hope that's okay. I do have tons and tons of calculations. I think towards the end of the chapter I should have more, but I never ask too many of these because I think students get these, and where you're confused is actually elsewhere. So anyway, I shut up. Thanks. Next up, we will talk about how to calculate the line integral of a vector field. And so anyway, thanks.